Hey, good afternoon, everyone. I hope you are doing all right and ready to learn some physics. So, we are, I think we are rather than we are, I think I should say we have already talked about the charges and we learned that rate of flow of charges is the current, right? So, we learn about that. And then we said, okay, when charges flow through a conductor, they experience some sort of resistance, opposition, like a friction kind of situation. We said, okay, that property is called resistance, and device that gives that kind of property are called resistors. So the notation is this wiggly line for the resistor, and we write R on the side. And then we talked about battery. Battery can have EMF, and when the battery does not have its internal resistance, then EMF and the potential it supplies to the circuit, they're going to be same. But anyway, we talked about battery and we learned that we can represent battery by drawing smaller and shorter lines. So this is positive, this is negative terminal of a battery. So now here we want to look at the complete picture. What happens when we connect them, battery resistor with the wires, okay? That has negligible resistance or zero resistance. That's what the circuit is. So we're going to be talking about electric circuits today. And our body is full of such circuit, okay? So cell membranes, they have charges and the charges creates potential difference. And that potential difference triggers the signal, okay, in our body. And it goes through these different sensory nerves, okay. So they are so complicated. So we can sometimes, arrange them something like this, what we call in series or in parallel. So this is circuit that exists in our body. Okay. So now what we're going to do is we're going to talk about simple circuits that we can use to model this kind of complicated system. Okay. So let's get it started. A simple circuit has a resistor that has a resistance R, and there is battery connected, and this is symbol of battery. So it supplies a potential difference of delta V, or we also call EMF, okay, for a source, for a battery. That potential difference could be EMF. They are equal when we neglect the resistance, tiny resistance that happens inside the battery. Everything has resistance, okay? Even these wires, connecting wire, they have some resistance, but their resistance is negligible compared to this device resistance. So that's why in most cases we neglect them. But if there is one, then we'll learn how to take care of that in next class, okay? And this diagram, you already saw this last class. So basically, this is just the stretched version of this circuit here. There is a battery, and let's say it starts from here, passes through a battery, and goes to the register, crosses the register, and comes back to the same point. So once it crosses to the register, it comes back to the same point, means these 2 points, they are basically same. So it is just the straight representation of that circuit, and it tells us how the potential changes in a circuit, right? So when there is this connecting wires, we say, okay, resistance is negligible, means the potential not gonna change. Remember, potential delta V is I times R. When R is negligible, the change in potential also becomes negligible. So we can say, okay, potential over here, whatever it is over there in the positive terminal of a battery, let's say 9 volt, then everywhere up to this end there gonna be 9 volt everywhere. Okay. And on this side, usually negative, we take 0 unless it is said, okay, it is negative 2.5 or something like that. So it is 0 all the way up to here. So what do we see is that the potential drop here. So we had 9 volt. So it goes from 9 to 0 volt when, let's say, current flows something like this. So that's what it is showing you. So let's say this is 9 volt. So it goes from 0 to 9 volt, just like 0 to 9 volt here in the circuit there. And then what happens? It remains unchanged where there is this, wire, connecting wire. But now it decreases to 0 once it crosses the resistor. And that's that. If there are more than one, then it does not, goes to 0 in one resistor. We'll talk about that situation as well, but this is a simple circuit situation. So how much current is flowing through this is given by Ohm's law. We talked about that last class as well. So I, or current, is delta V over R, or often we may also write delta V, or change in potential, is I times R. Okay, I think that's what I have written here. And for a battery, these two things, ideal means the resistance is resistance inside battery is negligible. So that's what that means. So that means this equation can be written in terms of EMF. Okay, same rule. Okay, so if we have a battery that says we have 1.5 volt battery, and that means EMF is 1.5 volt. But that if that battery has a negligible resistance, in that case, this is same as the potential difference it supplies across this device or resistor. Okay. So if you have ever opened the hood or look at the underneath the hood of car, there is a 12 volt battery. Okay. Oh. And we can write something like this. Okay. So this is a simple circuit. So when we have just one resistor, we can just use Ohm's law like this. And depending on what we know, we can find the third thing, okay? But we can have multiple resistors connected. And we call, for example, if we have this connection, one after another one, end to end, something like this kind of connection. This 3 dots means you can have many number up to n number, right? So that means this kind of connection is called series. So when we have this series connection, see, whatever current starts here, there is no other way to go, escape. So it's going to be there, 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 and there. Same current. So series resistance means same current. And what we want to do is to use Ohm's law. See, Ohm's law says, okay, delta V is I times R. So we want just one resistance. So that means we can combine these and get just one value. When we do that, we may call that equivalent resistance, because if we replace these 3 by 1, that is equivalent resistor. Okay. Then current in the circuit gonna be still same. It wouldn't change the current, so it wouldn't change the property or behavior of the circuit. So we can replace that by just 1. So for example, we are replacing these 3 by 1. So when we have 3, then we need to add those to get the total. Simple, right? They are in series, so we just add the numbers. So if this is 2, this is 4, and this is 4, and then this is going to be 2 plus 4 is 6, and plus 4 is 10. So in this case, there are only 3, I am assuming. But if we have 4, then we keep adding that one as well, and so on. So that's what it means, right? In series combination, equivalent resistance is found by adding them, simply adding those numbers. Okay. So unit of resistance is ohm, denoted by this uppercase sigma, Ohm's law, from Ohm's law. Okay. So that is called series connection. We can have parallel connection like this. So over here, rather than connecting one and then another one, it starts from the next end over there. What's happening is, see the R1 and R2. And now this R2 over here is connected between these two, basically terminals here, all of them. So this kind of connection is called parallel. So when we have that kind of situation, what happens is the potential here, potential here, potential here, it's going to be same, and that's going to be same as this one there. Okay. So if we want to use Ohm's law to find total current in the circuit, we want to find the equivalent resistance again. So reduce this to just like this, only one resistance out of these 3, 4, whatever we have. So how do we do that? For that, it turns out that we need to do this, and this can be derived by writing that delta V is same everywhere. So often what I see is students do this math and they think that is R equivalent. They forget the fact that that is not R equivalent. Rather, this is 1 over R equivalent. So that means you need to invert it. Okay. So often that's what happens. So they do this math over here on this side and say, okay, that is R equivalent. But remember, this is not R equivalent. It is 1 over R equivalent. So to find the R equivalent, what you need to do is you need to take the reciprocal, right? So for example, 1 over R equivalent, let's say this sum gave you 0.5, then R equivalent gonna be 1 over 0.5, which is 2. So, and that's how you need to do it. And when we have just 2 resistors, for example, let's say we have only 2 of these. We don't have that. Our circuit is just this. So that means we say, okay, there are 2 resistors in parallel. Okay. So in that case, we can rewrite this equation, simplify this. So these are fractions, right? So 1 over R equivalent. So over here, there is R1, there is R2. So maybe I can do this R2 here, R2 here, R1 here, R1 here. So that way this is, both of these are R1, R2. So I can take that down here. And then they're going to be R2 plus R1 or R1 plus R2, does not matter, same thing. So that is 1 over R equivalent. So R equivalent is product of these two, divide that by the sum. So what do we see? R equivalent is product divided by the sum when there are only 2 of them, okay? So often we'll be looking at, circuit that has just 2 resistors in parallel. So this may come out handy. And another interesting thing about this is, let's say both of them are same. Okay. R1 is R, you name the number, whatever you like. R2 is also R. Then what's going to be R equivalent? Let's calculate that. So R1, R2, both of them are R. So that means R times R is R squared. And then R1 plus R2. So R1 is R2 is R. So that means R plus R is 2 times R. So one of the R gonna cancels, giving us R over 2. So when we have two resistor that has equal resistance, same value, right? Then when we connect them in parallel, what happens? The equivalent gonna be exactly half of those two, okay? One of those, I should say half of one of those. And since both of them are same, doesn't matter which one is which. So you can try this by, let's say, saying one is R, another one is 2R. What's going to be R equivalent, right? So that I will let you try. But here I am asking you this clicker question. Oh, looks like I haven't started clicker yet. So let me start the clicker app. Okay, so it's ready. So I think you don't have to do much math here. So I'm giving you a minute and 30 seconds to complete this. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Here, let's see what we got here. So mostly B, 2.5, 1.25. So the resistor is doubling. So current is going half. Kind of makes sense, right? The only problem is that these resistors are in series. So whatever current it enters from here is going to be same everywhere. That's what we talked about, okay? Because current is flow of charges. So there is no other way to go. So it's like a water flowing in a pipe. There is no opening, okay? So they are not going anywhere. So same amount of current flows through that. So that means if I1 is 5 ampere, then I2 should also be 5 ampere, I3 5 ampere. So why are we supposed to know that? That's what we talked about here, right here, okay? So they are same, and looks like none of these have that kind of choice. So that's why E is the correct answer in this case. So probably some of you are thinking, you tricked us, Ramesh. Usually you don't give none of the above as the correct answer. Well, it may happen sometimes. Okay. Okay, so let's not forget, when resistors are connected in series, the current through each of those resistors are same. So I wanted to remind you, I wanted to make sure that you remember that, okay? So this question hopefully helps you to recall that. So now let's suppose we have series, two resistors in series, and here I'm just putting numbers there, and this I just snatched from my note. It's already done in my note. So there is this 12-volt battery. So delta B is 12 volt, or we can also say EMF is 12 volt. And then it says it's connected in series with 2 ohm resistors and 4 ohm resistors. So connected in series with 2 of them means, and that's how we draw them. Okay. So this is the statement and this is the sketch. Okay. What is the potential difference across each resistor? So delta V1, delta V2, let's say. Let's say this is R1, this is R2. So here R1 is 2 ohm and R2 is 4 ohm, and delta V is 12 volt. Okay. So now it's talking about what is the potential difference across each of those. So we can say, okay, potential across resistor number 1 is what? Potential difference across second one is what? And that's what I'm writing here in the circuit drawing, okay? So what we know is they are in series. So to do series circuit analysis, what we can do is we want to go from 2 to just 1 resistor. And since they are in series, R1 and R2 are in series, are equivalent, gonna be easy. 2 plus 6. Oh, not 6, 4. 2 plus 4 is 6 ohm. So that means what happens is we want to draw this circuit, and then next, once we have R equivalent, we want to draw this. Now, once we have this, we are ready to find current. So why do I need current? Because to find delta V1, we know. So you may be wondering why you are doing that, Ramesh. Because we know delta V1 is, according to Ohm's law, I times R1, and delta V2 is I times R2. So that means we need, so we know R1 and R2, so we need I, okay, to find delta V1 and delta V2, okay? So that's why we want to find current in the circuit. So how much current is flowing through the circuit? So for that, we need to first reduce this, and that way we can use Ohm's law, okay? And so now, using Ohm's law, in second circuit or reduced circuit, sometimes it's also called reduced circuit. So we reduce from 2 resistors to 1 resistor, right? Multiple resistors to 1. So now over here we can use Ohm's law. So current is change in potential difference over R equivalent. So here there is only one resistor. So whatever the potential we have from the battery, same goes there. Okay. So that's why it is 12 volt and this is 6 ohm, and that gives you 2 ampere. Unit of current is ampere. Ampere means voltage divided by ohm. Okay. So 2 ampere. So that current is 2 ampere here. And since both of these are in series, so whatever begins here, 2 ampere here means 2 ampere here, 2 ampere here. So now we know I, so that means we can go back and find delta V1, for example, is I times R1, so 2 ampere times, and R1 is also 2 ohm. So product of current and voltage is potential difference, and unit is volts. Okay. Now let's do that for delta V2, which is I times R2, which is 2 ampere times 4 ohms. So that gives me 8 volt. So what do we see here? Out of 12 volt, 4 volts went to this 2 ohm resistors and 8 volt went there. So total of 4 plus 8, total of these two is equal to delta V. So when we have series, it turns out that the sum of the voltages here and here is equal to sum of the voltage that is available from the battery. It makes sense. Remember, this is the potential energy per unit. It is potential energy of the charge. So that means this charge goes energetic here. So that means it starts with 12 volt potential. And then when it arrives here, what happens? It goes from 12 to 8 here. So 12 here, 8 here. So difference between 12 and 8 is 4 volt. And when it crosses this one, then we have now, see, it goes to 0, means there is 0. So difference between 8 and 0 is 8 volt. So it loses 8 volt energy, 8 volt equivalent energy over here, and it loses 4 volt equivalent energy. So actually to calculate energy, we need to multiply by the charge of an electron. Okay. So in that we know charge of an electron is 1.610 to the power negative 19 for value, right? So when we multiply this by volts, what happens? The energy we call as an electron volt. Okay. Rather than joule, we may say electron volt. I think we talked about this briefly. Okay. So when we are just talking about pure charges, the charge is going, like for example, charge of an electron, then it is just E. So when we multiply that by potential difference in volts, then that gives us energy in electron volt. So basically here, electron starts with 12 electron volt and it loses 4 of that, 4 electron volt here, and then loses the rest of the 8 electron volt over there. So that is a more accurate way of talking about, but we can say, okay, its potential difference changes by 4 over here and another 8 over here. That's another way to saying that, okay? The potential difference versus energy. So to get energy from potential difference, we need to multiply by the charge. Here, the charge that's moving is electron. Okay? So anyway, so even in the conventional sense, what happens? The electron or proton, they have same value of the charge. So the energy will gonna be same. Value of the energy gonna be same. Okay. So that's how we analyze circuit that has this resistance in series. Okay. So we need to go step by step, so multiple steps. So now here is a question very similar to that. See, over here I had a resistor done something like this. That's how it was connected over there. But this resistor, second resistor, could be going something like this as well, since there is only one path for the current. See, whatever current starts here, same current there, same current there, same current here. There is no other path. There is only one loop. Okay. So that's why the current going to be same, means they are in series, we can say. One end, so next end is connected to the first end of the next resistor, and so on. So it may look different from what we had over in the previous slide here, but it is basically same connection. Okay, there is no difference between this one and that one. Only difference is value of the resistor. Okay, so here R1 is 6 ohm, R2 is 12 ohm, so this is double of that one. So what is the potential difference across R1? Here delta V1 is what, and delta V2 is what. So the sum, just like we saw, sum was, what was the sum over here? 12 volt, same as the voltage from the source. Over here, source voltage is 9 volt. Okay. So sometimes we may just show something like this rather than drawing a battery here. So instead of that, we may just do that. Potential difference across A and B means it's just like uh, connecting a battery over there. Okay, so that's what that is. So this is 9 volt. So this 9 volt has to spread over there in those two. So how do you find that? So just like we did before, we want to find equivalent resistance, right? So delta V1 is I times R1. I is same for R1 and R2 because they are connected in series. And delta V2 is I times R2. So need I, just like before. Okay. So how about you folks go ahead and solve this problem? I'm going to make clicker question. Okay, I'm opening the poll, and you have, let's say, 2 minutes. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So B and C is mostly C. I hope that is correct. So first we find the R equivalent being in series. R equivalent is R1 plus R2. That means it is 18 ohm. And now the current is delta V over R equivalent. So delta V in this case is 9 volt. 18 ohm. So that gives us half ampere. So now delta V1 is half ampere times R1 is 6 ohm. So half of 6 is 3 volt. So this is 3 volt. So that means this is double. See, the resistance is double. Since volt is potential difference is I times R. So I is same. When you double the R, potential difference has to be double. So 3 here means 6 over there. So it looks like yes in this order. Okay. So here I said delta V1 and delta V2. So that's why this is correct combination than this 6 volt, 3 volt. But either way, most of you got it right one way or the other way. So that is good. Okay. So that's how we analyze circuits in series. Now let's look at similar example when they are in parallel. Okay. So same 12 volt battery. Now these are connected to parallel resistors R1 and R2. They are connected to parallel resistors. Okay. So resistor R1 has a resistance 6 ohm, 16 ohm, not 6. R1 is 16 ohm. R2 is 32 ohm. So looks like here did not ask what question is talking about. So that means we want to know what is this current, what is this current, what is this current, right? So they are in parallel with the battery, means this 12-volt battery gives 12 volt to this, 12 volt to this. Remember, this is the one feature of the parallel connection. The voltages are same. In series, sum of voltage was equal to the voltage of the battery. Over here, individual resistors going to have same voltage when they are connected in parallel. So that's why I'm writing in this case 12 volt over here, 12 volt over there too. So in this case, we can easily find what is I1 and I2 in this case. Okay, so let's do that. So since we know voltage right here and resistance right there, so that means we should be able to tell I1 is delta V1 over R1, and delta V1 is same as delta V, right? So this comes from the formula, and we know this being parallel combination, delta V1 is same as this delta V or EMF. Let's say in this case EMF. Let's use different notation as well. Let's get used to a different notation as well. So that means 12 volt divided by R1 is 16 ohm. Okay. 4 times 3, 4 times 4. So it looks like this is 3/4 ampere. Okay. So now similarly, I2 is now EMF over R2. And when you do that, you have 12 volt divided by 32. So voltage is same, but resistance double means current going to be half in this case. Okay. So it's going to be 3/8. Or 6 over. So anyway, so the total current in the circuit, I going to be I1 plus I2, because the same thing goes here and goes into different direction. So we should be able to add that. So that's going to be 3/4 ampere plus 3/8 ampere, right? So to make this 8, we need to do that. So it looks like it's going to be 6 plus 3 is 9 divided by 8 ampere. So when we do the math, looks like it's going to be around 1.1 ampere, something like this. So this is I did without finding the equivalent resistance. Okay. So when I did not find the equivalent resistance, so in this case, that was possible knowing that the potential across that resistor was equal. Okay. But what is the standard way of doing it? Find the equivalent resistance first. So equivalent resistance of 16 and 32. So how do you find that? So alternatively, 1 over R equivalent is 1 over R1 plus 1 over R2. That means 1 over 16 plus 1 over 32. So R equivalent, hey, when they are just 2, we can just multiply those two and divide by the sum. So 48. 32 divided by 3. It looks like that's going to be like that. Okay, so this is R equivalent. And this I have done in the note as well. Okay, so I'm just walking you through. So first, when you are just working with circuit, it's easy to get confused. Okay, so that's why I'm showing you here, and it is also in the note. You can go back and look at the note, but you have to be able to do it without looking anywhere. Okay, so you need to practice until you can do that, at least for 2 resistors. Okay, so here often, so let me talk a little bit about often a mistake is make in this kind of circuit analysis. So over here, what I did was I found this current I 1 by just using these numbers, or this number and 16 ohm, right? So I was able to do that because they are in parallel. So that means the voltage is same. But students tend to use that even when they are not in parallel. So for example, if I ask you to find current through this here, what is current? And if you just write 9 volt, let's say I1 is delta V over, let's say R1, if you do that, what's going to happen? 9 divided by 6. So this is incorrect. Why can't you do that? Because this delta V, or this 12 volt, or sorry, 9 volt, is not voltage across this resistor. They are connected in series, means the voltage across them may not be same. They split. We know that, right? So you cannot just randomly use this equation everywhere. So you need to be able to identify where you can use it, where you cannot. Where you can use it, wherever you know volt is right across that, okay? Or there is, when there is only one resistor in the circuit, only one resistor in the circuit. That's when you can just use Ohm's law, one step. But if you have more than 2, in that case, what happens? If they are in series, then of course you cannot do that at all. But when they are in parallel, then we know this is going to be same. So you can find current through this resistor just by using Ohm's law in that particular resistor. Okay. So do you know when you can use it, when you cannot use it? Directly, just one resistor and one voltage? Hopefully you do. So over here, you see there are these 2 resistors. They are connected in series or parallel. What do you think? So first, let me ask you that question. Are R3 and R4 connected in series? Or I should write, let's make R1 and R4 are connected in A, series, B, parallel. So I'm going to open the clicker question and you have 30 seconds to answer this. So I'm polling on this one here, not this one. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. Oh, we even have C and D. Okay, so over here, what do we see? 12 volt, 0 volt. So 0, see the connected wire, it does not change. So all the way up to here is 0 volt. All the way here, it is 0 volt. And over here, everywhere, up to here, 12 volt. And up to here, 12 volt. You see the same difference of 0 and 12, 0 and 12. So that means they are connected in parallel. Okay, they are connected in parallel. So if they were connected in series, same current would flow. But here, what's going to happen? Once this current arrives here, part of it going to go this way, and part of that going to go that way. So they split. Okay, it's not one continuous loop. That means it's not in series with the battery. Okay, so now let's suppose we figured out they are connected in parallel with the battery. So now, what is the current flowing through one of those resistor? Looks like both of them have same value. So what is this current here? Okay, so that's what this question is asking about. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly C. So is that so? So it is in parallel, so that means there is 12 volt here. So now we know voltage and resistance right there, right? So that means the current over there gonna be voltage divided by resistance. So yes, in this case, when they are in parallel, we can use this. But if they were connected like this, So let's say what is current through? And choices are still same. Okay. So what do you think? You have a minute and 30 seconds. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got. We have everything here. A and B are competing. Okay. So good thing many of you did not just do 12 volt divided by 4, right? That would have been 3. Looks like some of you still did that. So you cannot do that because now see here 12 volt. Over here there is 12 volt. But 0 is over here. So what is voltage here? We don't know. So that means we don't know the potential difference here. So the potential difference across R1, we don't know. It is not 12 volt. So that's why you cannot just say 12 divided by 4. Okay. So you need to go through. So now being in series, both of them, there's in this whole circuit, only one current flows. Okay. One value of current flows. So that means we need to reduce this to just one R equivalent. And R equivalent in this case, they being in series, we have just 8 ohm. 4 plus 4 is 8 ohm. So now we know this and we know that. So that means only one resistor now means we have current is this voltage divided by R equivalent means maybe I should write delta V first, formula first, and then now 12 divided by 8 means 1.5. So it looks like A is correct answer here. Ah. How did you get 2 ampere? Can someone tell me? Maybe we need a break. So let's take a break. I'll see you in 5 minutes. Welcome back, folks. So now you see there is another question on the screen. So I am starting the poll. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So it becomes half based on many of you. Okay, so how do I do it? So before it was open. So open means no current flows through this. When open. So that means we have just this circuit here. Just one resistance and that. So what is current then? 120 over R. We don't know value of R, so I'll just leave it like that, okay? Now when closed, then they're going to be current. And this is R. So this and that, both of them are in parallel with 120. Same resistance means same current gonna flow through them, okay? But is that be the same as what we had before or not? So for that, our circuit now gonna look something like this. Or if I were to redraw, it's gonna be one going like that, and the other one. So that's what we have now. Both of them are R. And when two resistors are in parallel, the equivalent resistance gonna be half of those. Okay. So 1 over R equivalent is 1 over R1 plus 1 over R2. And I know we talked about this. When both of them are same, this is going to be R. This is going to be R. So this is going to be 2R over R. So R equivalent going to be R over 2. Okay. So that's that. So now what is current then? New current, when it is closed, is that potential difference divided by the resistance, which is half of what we had before. See, this was R. Now this is R over half. So this is 120. Fraction of fraction goes up there and that. So this is 2 times R. Okay. So it doubled. So the circuit draws more current from this one here, from the source. So this is like a, so the current, whatever it was going, it does not change even when this is broken, okay? So that's why if we have two light bulbs in a room, if one bulb goes off, the fuse of one of the bulb goes, or let's say the coil burns, then in that case, what happens? Another bulb remains, as if nothing happened to the other one. So the other one does not affect the first one. Okay. So that's the beauty of connecting in parallel. So we still get that I, let's say, and now when it is connected, it draws more current. So since the resistance is same, both of them are drawing same current. So it's like saying we have 260-watt light bulb in a room. So that means both light bulbs are drawing same current, okay, from the source, same amount of current. So I here, so that means total is 2 times I over there. So here resistance did not double. Since they are in parallel, resistance did not double. Resistance became half, but current double because of that. Current and resistance, they are inversely related according to Ohm's law. Okay. Okay, with that, now let's look at this one. Now there are 3 resistors, okay? So it's like saying, okay, we are connecting something here, although it's not shown and does not have to be shown. So we may be connecting a battery, something like that, but there are 3 resistors. Notice these two are same, and this is half. So I'm opening the poll, and you have 1 minute and 30 seconds to answer. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So we have all of those, slightly more for A, B, and C. They are competing. Okay. So equivalent resistance. So they are connected in parallel, see? So they are connected in parallel. So 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3. So we can do half plus quarter plus quarter. Quarter plus quarter is half. Half plus half is 1. Oh, yes, that is 1. So R equivalent is 1 over 1 is 1. Okay, so that's one way to do it. So even without using formula here, you should be able to do it because these resistors are given so nicely. So these two are in parallel, of course. So that means they are same. So when we connect two resistors in parallel and they are same, the equivalent going to be half of one of those. So it's like saying we have one of that there and the other one, combination of these two, it's like saying we have 2 ohm, we have 2 ohm. Okay, so these two, combination of these two gives you 2. How do I know that? Both of them are equal. And when we connect two equal in parallel, the resulting gonna be half of one of those. So half of 4 is 2. So now what do we see? We have 2 and 2. And half of 2 is 1. Oops. So that's how you can reduce as well. If you do not want to do that math, when you have nice combination like this, okay? So we have A as the correct answer here. So now I have second portion here that says, okay, so if we connect a 8-volt battery, just like I was saying, at A and B, let's say 8-volt, what is the current? So now from before exercise, we learned that equivalent is just 1 ohm. And now we have that 8-volt battery. So that means delta V is this and R is that. So the current gonna be, here is talking about current over here, means the current before it branches out, okay? So we're talking about this current, not that, not that, not that. So 8 ampere current goes there. And then now this is split into 3 branches, I1, I2, I3. Okay. So since they are connected in parallel, finding current through each of them is easy because when they are parallel, they're going to have same voltage, 8-volt here, 8-volt here, 8-volt here means they're going to be 4 ampere and they're going to be 2 ampere and they're going to be 2 ampere. So 2 plus 2 is 4 plus 4 is 8. So I is same as this combination of I1, I2, and I3. Okay. So that's how it works out, folks. So what is the current through its resistors? We just talked about it. Okay. So now we can have combination both series and parallel at once. So far we talked about separately, one being in series, another being in parallel, and so on, right? But now we have these two in parallel, and this one is in series. But since this is in series with this, now we cannot say, okay, these two are parallel to this, and whatever voltage we have, which it says 12 volt, is not same as 12 volt here, okay? So this is not 12 volt because part of that cost drops here and the remaining goes over there. So now if I ask you what is the current through I2, what is I2 here? Let's say what is current through R2? So I2 is what? And you say, okay, let's use Ohm's law. I2 is delta V over R2. And you calculate that, that's going to be incorrect because this is not going to be same as this one there in this case. Because there is another resistors in series. So how do we do that? First, we need to combine these two. These two, see over here, these two are connected here and connected back here. So these two, I2 and I3, they come here and recombine, okay? And over here, the same current is split into two. So we can say, okay, these two are in parallel to each other, okay? So that means we can say, okay, so let's see, our delta B, or in this case, it says EMF. So let's say EMF is 12 volt, and it says R1 is 4 ohm, and R2 12, R3 is 6. So if you are wondering why there are some zeros after decibel and some there is not, basically it's just two sig fig problem here, okay? So those are the things we know, and it's asking us what is this, what is that, and what is that, current through each of those. And I'm denoting current through R1 as I1, current through R2 as I2, and so on. Okay, so that's what I am doing. So now, first, what we want to do is we want to reduce this. So since these two are in parallel, we can go from here to here. Let's say I'm kind of going kind of backward here. So I'm copying the EMF. I'm copying the R1. And then now I have this R2 and R3. I think this is the example problem I picked from the book. So this is equivalent of 2 and 3. This is not equivalent of every resistor. So sometimes I like to write something like this. So this is equivalent of R1 and, sorry, not R1, but R2 and R3. Oh, so that means I should be writing 2, 3. So this does not means 23, okay? It's the equivalent of 2 and 3. That's what that is. I'm writing that in short. So now we have this kind of circuit, okay? So now these two are in series. So whatever current flows through this, that's going to be I1. And we can calculate that using S2. But what is R23? So 1 over R23 is 1 over R2 plus 1 over R3 using, see, knowing that these two are in parallel, right? So, oh, not a very good combination looks like. So R2 is 12 and R3 is 6, okay? So 1 over 12 plus 2 over 12, means 3 over 12 means R23 is 12 over 3 is 4 ohm. So this is 4 ohm. And what is R1? Oh, R1 is also 4 ohm. So now after this comes this one here. So let me make a little room here. So now we combine those. So now we have R equivalent. Okay. And what is that? That is the series of these two means it is R1 plus R23 means it is 8 ohm. So now we can tell what is I1. I1 is same as whatever it goes through that. Okay. So that's going to be I1. So I1 is delta V over R equivalent. And delta V in this case is 12 volt or EMF 12 volts, same as delta V. And R equivalent is 8 ohm. So that means 12 means 1.5 ampere. Okay. So now we know I1. Now we need I2 and I3. Okay, so the same 1.5 flows through I2 and I3. I mean R2 and R3. Okay. So now how do I do that? So now from here we can do it two different ways. One, I think I have done in the note where I do, okay, now there is this I1 and R1 we know, so that means we know delta V1, which is 1.5 times 4 is 6 volt, right? So if it is 6 volt over there, they're going to be remaining, see 12 minus 6 is 6 volt here. So that's how it's going to split. And that makes sense because this is 4 ohm, this is also 4 ohm. So equal resistance, same current, same voltage. So 6 volt and 6 volt. So now since these two are parallel, each of them have 6 volt. So that means now you can use Ohm's law using 6 volt as a delta V and resistor, whatever resistor is there and whatever resistor is there. That's one way to do it, okay, which I have done in the note. Now I'll show you another way you can do it. Another way is knowing that voltage, since R2 and R3 are parallel, what do we know? Is that, let's see if we can do that in one step. So that means delta V2, which is voltage across, let's say R2, let's say that is delta V2, and delta V3 here. Since these two are in parallel with each other, this delta V2 and delta V3 are going to be same. So that means I2 R2 is I3 R3. Voltage across 2, this means current through this I2 times that resistance. Okay. So you can always use Ohm's law in one particular resistor. If you know what is current or trying to find current, voltage, and resistance. If you are using current, voltage, and resistance combination in that particular resistance, then you can always use Ohm's law. So that's what I'm doing here. So now we know the resistors, but we don't know the currents. So let's say I2 divided by I3 is R3 divided by R2. So now from here, you will get a relationship between I2 and R3. Sorry, I3. So R3, what is R3? 6. And R2 is 12. So 6 over 12 means it's half. I2 is half of I3. And another thing you know is I2 plus I3 is same as this current that goes through this one, I1. So you can use that one too. So now with these two equations and knowing this, so unknowns are just two, so you should be able to solve that. So whichever you find easier, you can use it, okay? But the result should be same. One that I completed in the note versus this one over here, okay? So for example, if I were to complete calculation, I2 is half of I3 and I3 is I3 and that is equal to I1. I1 is known. So this means what? So 2 plus 1, 3 over 2 I3 is I1. So I3 is 2/3 of I1. And we know I1, we calculated I1. So that means now we know I3. Once we know I3, we can plug that I3 in over here or over there. I guess this is going to be easier. So I2 is half of I3. Okay. So you need to be comfortable looking at circuit and see how the current and voltage distribute using the knowledge we just learned today and then do it. Okay. So now over here it says what is the current through 12 ohm, just like we did that previous question. Exactly same. But the problem is we don't know delta B too. We know delta B, okay? Delta B here is 276 volt. That's how it is connected over here. But we don't know delta B too. So that means we can use this, but delta B2 is not same as delta B because delta B2 is not directly in parallel with this battery here. So that means you need to simplify the current, and that's what I'm doing, just like I did in the previous, okay, case. So here, this is 24, this is 12, right? So these two are in parallel with each other. One is 12, another one is 24. They are in parallel. So what is the equivalent resistance? So here is the pole, okay? You have a minute and 30 seconds to pull on this. So basically, it is same problem with just different numbers. Same problem as what we did before. Okay, 30 more seconds. Five more seconds. Five, four, three, two, one, and it stops. Okay, let's see what we got here. So B and C kind of competing. Okay. So when two resistors are in parallel, what happens? The equivalent resistor going to be smaller than the smallest one. So that's why the 18 is not correct answer. It is correct answer. So use formula and figure that out, folks. Okay. So this is 8 ohm. So it's like saying now what I have is there is 8 ohm. And over here, this is 276 volts. Okay. So that way, now I can tell what current is flowing through this one, which is same as whatever current flows here. Okay. So now this current, if I say this is I1, then I1 over here gonna be this delta B, and R1, which is, oh, not R1, sorry, R equivalent. So 276 divided by 8. Oh, do I know how to do that? 8 times 3 is 24, and 3, and then 36. Ooh, 34 point something, 34.2 something. So that way we find the current. Now, see, this current is not I2. So to find I2, we need delta V. So now, once we know what that is, uh, what's the voltage over here. So knowing this current and this resistance, we can tell the voltage, okay? And so that means we can do this. So now, delta V1 over here is this, delta V1. And delta V23 is basically this one here. So now, once we have this, we are going backward. See, we went like this, and then now we are reversing back, okay? So it's kind of goes in a cycle, looks like, because we first went through this to find this. Once we have that, we have this delta V1. So that means to find delta V2, basically that's going to be same as delta V23 because these two are in parallel, okay? So I can just do this. Move this delta B1 in that side, so I have delta B2, 3, or that is also same as delta B2. So here delta B1 is I times R1, so I need, we need I, so that's why we went through this, okay? So once we have that, oh, that is the calculation we were doing, I think. So what current did you find, folks? Did you do this calculation here, this? And that should be the answer here. So let me poll you on that one. And you have only 30 seconds. It's just dividing one number by another number. Hope I got this one of those right. Or if you don't see exact, hold the closed one. Hmm. May not be closed. Any one of those looks like. Okay, I'll be closing in 5 seconds here. 5, 4, 3, 2, 1, and it stops. Looks like I don't have answer over there. Many of you chose 12. And how did you do that? Maybe you divided 276 by 15. There should be none of those response here. Remember, this I1 should be same as this one over here. So 276 divided by 8. So it looks like I don't have answer on the choices. My bad. 276 divided by 8 should be the answer. Okay. So it looks like the correct answer in this case is an R equivalent 8 ohm. So this was 12, this was 24. So yeah, this is 8. So 276 divided by 8 is not 23. Looks like it is. I use my calculator here in my computer, and none of these are correct answer here, folks. Okay, so once we have this, voltage over here, now we can find delta B2 by using this formula over there, okay? So for that, we need B is I times R1. So 34 times 15. So this times 15, let's see how much is that. Oh, something is wrong. What number is incorrect here? So 12 and 24. Is that 8? Is that correct? R2, 3. Did we get that right?
Professor,
Yes.
I chose C for R1 because in the last problem, we did R2 plus R3, and then once we got that the inverse of that answer, we then added the 15 ohms to it.
So this B1 is I times R1, or delta B1 is I times R1. But for that, we needed to find, let's see, I. And we had, did we find I before? Oh, this is the I we are finding, right? See, we don't know delta B1 yet. So that means we need to find the current through this circuit, whole circuit. And for that, we need equivalent. So is 8 incorrect here? So let's see. Something went wrong. 288 divided by 36. It is 8. So that means this combination of, oh, I see. I see what you are saying. So this supposed to be R23. Yeah, I know what I made mistake here. So that's supposed to be 8 ohm, supposed to be, oh, this supposed to be 8 ohm. And then now for this, we need 8 plus 15. I think that's what you are saying. Okay. Oops. So this becomes 23 ohm. And with that, I think this becomes the, oh, so this total is 23. So what is current then? Right? So current is 276 divided by 23. Oh, okay. So over here, what I did was I kind of went from here to here and said, okay, that was it. But that wasn't 8. Rather, R23 was 8. Okay. So my bad there. And to find R equivalent, we need to add this R1 and R23. And that gives us 23. That's the mistake I made. So now with 23 and 276, we should have, so 276 divided by R23. Now looks like 12 ampere, yes. Yep, that's that. Okay, let me choose that. And once we have that, we can now reverse and go back and figure out delta V1. And once we have delta V1, we can have this one there. Oh, it's 53, 51 already. So let's do it quick then. So delta V1 is I times R1, which is 12 times 15. So times 15 is 180. So volt. So that means now using this one over here. And by the way, this delta 2B3 is same as delta B2. So let me just write delta B2, which is now delta B minus delta B1 means 276 minus what we just found, 120 volt. And now once you have that, you can use this formula, okay? Okay, so yeah, it's a 2-minute more than our usual time. So we're just gonna leave it here and we're gonna pick it up from, next slide for the next class and gonna move to the more circuit analysis.